Derivation of momentum operator. Operators have no meaning on their own, only useful when applied to something. Basic school operators are sum, which is plus, difference, which is minus, product, which means times, quotient, and that means divide. 7 plus 2. Plus is the operator. 7 and 2 are the operands. We now know that 7 plus 2 will be equal to 9. So you can see the plus has a meaning here. It's adding the two operands together to get 9. But plus on its own does not have any meaning. In quantum chemistry or quantum physics or mechanics, operators have to wear a hat to recognize them as operators. Here are some examples. Here is position operator. This is X, it just means displacement. Displacement is distance with direction. So that's the operation for position. This is operator for momentum. This is what we're going to derive today. And this is in the direction of X. And that's why it's indicating the subscript here is indicating X, meaning that is a momentum operator in the direction of X. It could be in the direction of Y or Z or tau, which means three-dimensional operator. This is velocity operator. This is kinetic energy operator. And this one is angular momentum operator. This one here, H, is the Hamiltonian operator, which is the total internal energy of a system. And the total internal energy of a system is the kinetic energy plus the potential energy. And that's what we call Hamiltonian operator. Because we're describing the function of a wave of a particle, we start with this simple equation. The equation E I theta is actually cos theta plus I sine theta. And this is describing something called Euler equation. So in order to generate this wave equation of a particle, we basically add a constant to it. So there's a constant here to try and change it so that it looks like an equation of a wave. And therefore, we're trying to solve this. So the idea now is to change this angle. This is an angle. This is called displacement, angular displacement. So we're going to change this angular displacement from theta to x and t. So what I'm going to do now is to write that down as we know that x is basically a position and which is what we call displacement, and that's measured in meters, and t is time, and that's measured in seconds, and we have I, which is what we call iota. It's a Greek letter, and that's basically a complex which is root minus 1, and that's what we call a complex number. Complex number are imaginary, so imaginary. For instance, if you have a complex of A plus IB, so you can see that the I here is the imaginary, which is root minus 1. Theta, and so theta is what we call the angular displacement. So theta is the angular displacement. So let's say if you start from a point and you go in that direction, and so you would start from there and you end up there. So you start from A and you end up in B. So you've generated an angle theta, and let's say that was your radius, and this is the length of distance that you travel. So you can see that theta, so that's angular displacement. And from there, we can then write the definition for angular displacement because it would generate angular velocity. So angular velocity, which is what we called omega, that's omega, and that's called angular velocity. You're also familiar with basic linear velocity and also linear displacement and time, because that linear velocity, let's call that v, and linear displacement, let's call it x, so that's linear displacement, and time is t. So we can say v or c, because you can call velocity v or c, so we can say that is equal to the displacement or linear displacement over time. So that's the way we write the linear velocity, linear displacement, and time. We can do the same with angular velocity as well. So angular velocity is basically angular displacement over time, which means I can rearrange and make angular displacement the subject, and that would be theta equals omega t. So with our equation, which is wave equation we're trying to write out, that's our wave equation. Remember, x is a displacement, which is space, so that's space. So that's coordinate in space, and this one is time. And that is, we said, a constant, the exponential function I, and now that's theta. So I'm going to change the theta with omega t. So therefore I can rewrite it as the wave function xt. Then it's a function of displacement and time, which is a e I omega t. So what we're trying to do is we are trying to change the theta to make it have component of x and t, because it's very difficult to work on it if you have three different components. So we want to change that to have x and t. So that's what we're trying to do here. So this is the first achievement of doing that. So we've gotten rid of the displacement, angular displacement, and now we now got the angular velocity and time. So we got the time in there. So we now need to find the x. So now this is the equation we've arrived at. So we need to progress from here by saying that, so now what we need to do is work with omega t. So what is omega t? So that's omega t. Well, omega t is what we need to work with. But omega itself, if I write omega itself, is 2 pi f. And 2 pi f, there's another basic equation in physics which says c equals f lambda. So I'm going to make f the subject here. So therefore I get f equals c over lambda. So now what I'm going to do is replace that here and put it in there. And so I'm going to get omega equals 2 pi c over lambda. But also I'm aware of the displacement, velocity, and time, which we said that c is x over t. So that's the displacement. So I'm going to take that one, the displacement, and I'm going to put it in there. So therefore I'm going to get omega equals 2 pi x over lambda t. And altogether, what I'm going to now do is take this equation here and feed it into there. Right, so now I can write my new expression, which is psi. So this symbol here is actually called psi. It's a Greek letter. And so I'm going to write psi x t, which is a wave function. So that psi is basically what we call wave function. So we're trying to derive the function for the wave that we're going to use to then create this equation we need. So psi is basically A, E, I. Now I'm going to put that in there as my omega t. But before I do that, before I put that into there, I now know what my omega t is. So let me just write the omega t first, because omega t here, let's use a different color there. So omega t is basically now 2 pi x t over lambda t. You can see the two t's cancel out, which is 2 pi x over lambda. So that's what omega t is 2 pi x over lambda. Write this out now. So omega t equals 2 pi x over lambda. But let's call 2 pi over lambda k. Therefore, we can say omega t equals kx. So that's much easier to work with. So what I can do now is I can then say, well, that can then become kx minus omega t, and that obviously equal to 0. So what I now need to work with is I'm going to change the omega t with kx minus omega t. So the new equation we're going to now use is going to be kx minus omega t. Omega t, so I'm going to put kx minus omega t. So that is a new equation we're going to use now. We're going to carry on with here. So that one here, so I'm going to work with this one. So I'm going to just put a line there. I'm going to work with that now. Particularly, I want to focus on this one here. So we got psi xt, which is equal to a constant e I open bracket kx minus omega t. So we've achieved the first point that we need to do. We've changed the theta here into kx minus omega t, which is, I've got the t there, I've got the t here, I've got the x here, and I've got the x. So we've achieved that. So now what we need to do now is to write out k and omega and change those. So let's do that. So we know that k equals 2 pi over lambda, and we know that omega is also 2 pi f. But talking about Louis de Broglie, because we're talking about de Broglie wave matter. So we're talking about de Broglie, we're talking about the Broglie wave, which states that lambda is equal to h over p. In this case, this one is called lambda. That's the symbol, Greek letter, which basically means wavelength. And got h, which is what we called Planck constant, which is 6.626 times 10 to the power minus 34 joules seconds, and P is basically momentum. And that is mass times velocity. So what we're going to do now is make lambda the subject. So that implies that here, I say, we know lambda is the subject, so I'm going to change the k. So now k will be equal to 2 pi over h over p. But that can be written as 2 pi over h times 1 over 1 over p. 1 over 1 over p, 1 over 1 over p is p. Therefore, we can write that as equals to 2 pi p over lambda. So what I'm going to do is take that k and put it there, because k is 2 pi p over lambda. I'm going to put that in there. Now I need to talk about the omega here. Max Planck, that says energy equals hf. Max Planck in 1900 and Einstein in 1905 verified this equation. They proposed this equation. So therefore, what I'm going to do now is make f the subject. F equals E over H. F equals E over H. And therefore, I'm going to put that into here. So I'm going to put that into there. And therefore, I'm going to get the omega now. So that will become 2 pi E over H. Again, so I'm going to now take that one. I'm going to take that and put it into there. So that's omega. And I know what k is as well. So I'm going to take the k as well and put it into there. So now the final equation we're going to get, let's write it out now. So we're going to get psi xt, which is now equal to a constant E, I, open bracket. So I got 2 pi px over h minus 2 pi et over h, close bracket. There's a common factor here, 2 pi h and 2 pi h. So I'm going to take this out. So I'll get psi xt. That will be equal to a e I 2 pi over h, open bracket, px minus et, close bracket. Now, the px, so just to say, px has the same unit as h, et has the same unit as h, which is hr is Planck constant, and the unit is joules per joules seconds. So that's the unit, joules seconds. So that means the dimension is correct. So therefore, they're the same dimension. So it's easy to subtract them. So that's good. And if you look at Werner-Heisenberg uncertainty, and that actually says that change in momentum and change in position is greater or equal to h bar over 2, reduced Planck over 2. So talking about the reduced Planck, so that's reduced Planck. So talking about that, there's a formula that says that h, reduced Planck, is equal to h over 2 pi. and that's reduced Planck constant. So the h bar over 2 is reduced Planck constant, and it's represented as this. I'll call it h bar. So if I do 1 over h bar, or reduced Planck constant, and that would be 2 pi over h. And I already have 2 pi over h here, so which I've taken out as a common factor. So I can replace that by 1 over h bar. So that's just wave psi xt, and that's equal to a constant e I over h, a reduced Planck, and then that would be px minus et. So now we're getting towards the end now. This is what we now need to differentiate. So while we've got this equation that we need now, so this is the wave function that we need. So we need to differentiate this, and with respect to x, because I've got two variables here, t and x, and I've got x and t variables here, but I only need to differentiate it with respect to x. I could also differentiate it with respect to t, but that's for another time. So let's do that. So this is the function that I want to differentiate. So let's quickly talk about differentiation of exponential function. So if you have an exponential function that says a function y equals to, let's say, k, e, I, and x. So this is an exponential function. The differential of that, it will be dy over dx, since I'm differentiating with respect to x, and that will become, so I'll write this because that's y, so I'm going to write as d, obviously that's k, e, I, and x over dx. So that's what we're doing with differentiating, so I'll put it there. So, but what I need to do now, because that is a constant, I need to take it out here, because a constant, you don't need to differentiate that because it's a multiple of a constant. So I can carry on and write that as k, d, e, I, and x over dx. So that's what you do. You take the constant out, and then you just differentiate the exponential function. And now, when you're differentiating now the exponential function with respect to x, so let's call that dy dx. So that's dy dx. So what you're going to get now, obviously the formula you use for differentiation, if you have y equals to x to the power of n, and then dy dx is going to be nx n minus 1. But this is exponential function. If you differentiate exponential function, you get exponential function back. So I'm going to get k, yes, I'm not differentiating that, that's just a constant, but I'm going to get the e, I, and x back. And then when you get that back, and then you want to times it by, I want to times it by the differential of what's here with respect to x, the differential of e function. So I'll be timesing it by in, because if you differentiate I and x, I just get in, x disappeared. And so finally, you can then see what you've done is that your dy dx becomes, well, you get the same function that you would start with, because if you look at that, that's the same function you start with. This is your y. So you actually get your y back in that sense. So you get y and then in. So that's the same thing that will happen to this one here. That's what we're going to do here. Same thing's going to happen. So now I'm going to differentiate this. There are two variables. I'm just going to differentiate it with respect to x. Because I'm differentiating it with respect to x, I have to use something called partial derivative. So because we're differentiating with respect to x, keeping t constant as t, we use partial derivative, which is called partial derivative or partial differentiation. So now this is it. So now I'm differentiating this function here. So now I've written the partial derivative of the psi, the wave function, will be equal to a. So I took the a out because a is a constant, so I'll put it outside. And I'll put the function that I'm differentiating in here. All right. And so therefore, but because I'm differentiating with respect to x, not t, so this will be 0. If I differentiate that, it's a constant. And if I differentiate px, and that's x power 1, I'll just get p. And p times I over reduce Planck is what I'm going to get. So the final solution would be the same function here. I get the same function. So I get the a. So I get the a e I over h reduce Planck, open bracket, px minus et. So I get the same function back times by the derivative of what's here. And that derivative of that is basically I over reduced Planck p. But this one here is basically the actual wave function psi. So that's the psi there. You can see I got psi back. And therefore, I need to write that as psi I over reduced Planck p equals to partial derivative of psi with respect to x. So now this is the final equation I'm getting, and I now need to cancel out the psi on the left, on the right, and on the left. And so what do I get next? So I said I get this equation, and I'm going to cancel the psi on the left and on the right. It's a common factor there. So therefore, I'm going to get partial derivative with respect to x will be equal to I over reduced Planck p. But I need to make p the subject. So what I need to make p the subject, so I'm going to get p will be equal to, well, reduced Planck over I times partial derivative with respect to x. So now that's my momentum operator. So all I need to do now is take a hat on it to indicate that that's momentum operator. And because I'm looking at this momentum operator in the direction of x, I have to put a subscript for the momentum operator here to indicate the direction, this direction of x. So also do remember that I have 1 over I. Here it's 1 over I. And we know what I is. So I need to rationalize the denominator because that's a complex number in the denominator here. But I need to rationalize that. In maths we do. So in order to do that, I need to multiply 1 over I times it by minus I over minus I. So that's the rationalization process. But the I, we cancel I, right? So basically what I do get now is I get 1 over I times I over I, which is I over I squared. But I squared is root minus 1 squared, which is basically minus 1 to power a half all squared, and that is minus 1 to power 2 over 2, and that is minus 1. And so therefore I squared is minus 1. If that's the case, I can finish up here by saying that equals to, well, this one would be I over minus 1, which is minus I. So 1 over I is minus I. So let's write it here again. 1 over I is equal to minus I. So I can finish this equation here by saying that equals to 1 over I is minus I, reduce Planck, partial derivative with respect to x. So the P x is basically either minus I reduced Planck partial derivative with respect to x. So you will see the equation written in two ways. Like that, it's very common, the momentum operator, or like this way, which is also very, very common. It depends who's writing it. So either, both of them, you can write it either way. So that's the momentum operator, and that's the derivation of momentum operator. You can use your momentum operator to then derive other stuff, like for instance, so if I write the momentum operator now, right, you can write it in terms of y, and that will be minus I, reduce Planck, partial derivative with respect to y, or you can say P tau, which is minus I, delta A, reduce Planck, partial derivative with respect to tau, or you can write it with any of the coordinate. Tau is basically x, y, and z, so that's a three-dimensional coordinate. But you know that momentum is mass times velocity, therefore velocity will be momentum over mass. So which means I can write velocity operator as minus I reduce Planck over m partial derivative with respect to, well, let's say x now, because I have to put x there. And the same thing if you're doing kinetic energy. So let's say you want to write kinetic energy. So KE is a half mv squared, and that can be written as p squared over 2m, because I can change the mv, square the mv, and divide it by m, I get that, and divide it by 2, I get that. So which meant that I can basically do the same to this one here, the momentum here. So I got the momentum, so that would be, well, I need to square these ones. So if I squared minus I get, well, I squared is minus 1, we just done that. Minus 1 squared here is 1, so I'm going to get minus. So if I squared h here, because I'm using this one, so it doesn't matter, you can use any. So if I squared h, so I get h squared, and I have to square that one too. So basically what I'm going to get is h squared, right? And I've got my 2m, I'm only squaring p by the way, but I've got my 2m, so I'm going to stick the 2m there, and then partial derivative squared over partial derivative with x squared. So that will be the kinetic energy momentum. So that's how you find that. And there's more you could do with this. And then from then onward, we can write the Hamiltonian operator is basically T, the kinetic energy and the potential energy. And that can be written as, we know what the kinetic energy is, minus H, minus reduce Planck over 2m partial derivative squared with respect to x squared plus v. That's Hamiltonian operator. So yeah, there's a lot you can do with this. So that is the derivation of momentum operator right there.